All right, so when you have a chemical reaction that is in the state of equilibrium, you know that the forward reaction and reverse reaction are both taking place at equal rates. Well, when a system is in equilibrium, sometimes there are changes that take place and they kind of alter the equilibrium state a little bit. So LeChatlier's principle states that when a system is at equilibrium, if it is subjected to a stress, the reaction occurs so as to reduce the stress. Now, what stress means is changes. And there are three particular changes that we're going to discuss. The first type of stress, or the first type of change, is when we add or remove something, or like changing the concentration, like if I increase the concentration or decrease the concentration. So, for example, let's say that we have this reaction and it's at a state of equilibrium. So we have two hydrogen iodide and it's forming hydrogen gas and iodine gas. If we add some hydrogen, right? So let's say that we just kind of open up a valve and pump more hydrogen into the vessel where this system is at equilibrium. We now have an imbalance. And so you got too much hydrogen for this to be at equilibrium. So what's going to happen is, in order to get back to equilibrium, the system is going to try to get rid of this extra hydrogen, and that means using it up. So if it uses up the hydrogen, because that's going to cause this reaction to go backwards, because in that regard, hydrogen would be a reactant for the reverse reaction. So it's going to shift to the left. If it shifts to the left, the result is that the concentration of hydrogen iodide increases, because hydrogen iodide is the reactant. And remember, we said that this was going to go left. If the reaction goes left, that's going to bring down the hydrogen concentration, and it's going to decrease the iodine concentration, because in the reverse reaction, iodine is a reactant. So what about if we remove hydrogen? Let's say that we had a specific method to remove hydrogen. In that case, removing hydrogen, the system's going to try to replenish whatever was removed. Okay, so in order to do that, it's going to favor the forward reaction, and it's going to replace hydrogen. And the result of replacing the hydrogen is that it has to use up the reactant, hydrogen iodide. So the concentration of hydrogen iodide will go down. The concentration of hydrogen will slowly be replaced. And because the reaction is moving forward, the iodine concentration is going to increase. So you can kind of think of this as a teeter-totter. Reactants, products. And if the balanced state is what we call equilibrium, if something is removed, so let's say we removed R, we are no longer balanced. So the only way to get this to be balanced again is to shift whatever is R and add to more product side. And if you keep doing that, eventually you will have a state of equilibrium again. All right, so that's what happens when we add or remove reactant or product, and that means changing the concentration of them or adding or removing. So let's talk about the second type of stress, which is changing the volume or changing the pressure. Now first, we need to specifically state that this only applies to gases, or I should say only for gases. Okay, so if your equilibrium is mainly aqueous, then this does not apply. There's no effect to an aqueous equilibrium. This only affects gas equilibrium. All right, so you know that when you change the volume, right? Because if we think about any concentration is usually the number of moles over volume. So if we increase the volume, what does that do to the molarity? Well, you're dividing by a larger number, and so now your molarity goes down. Okay, so changing the volume of a gas, in effect, lowers its concentration, and vice versa. If you decrease the volume, then you increase the concentration. So let's take this first reaction here as an example. N2O4 breaks down and forms 2 moles of NO2. If we increase the volume, then there's just not enough, there's not high enough concentration anymore to be at equilibrium. So what the reaction is going to do is it's going to favor the side which produces more moles. Notice the coefficients here. There's more moles of product NO2 than there are of N2O4, right? There's only 1, so it's 1 versus 2. So by shifting forward and producing more moles of molecules, then that fills the space better. So if we increase the volume, the reaction will shift to the right, and it's going to try to fill the extra space. What if we decrease the volume? If we decrease the volume, essentially what we're doing is we're squeezing it. We're squeezing the reaction. And if we squeeze it, the system's going to prefer the side of the reaction which requires less space. Notice how the N2O4 only has 1 mole. 1 mole requires less space than 2 moles. So the reaction is going to shift to the left so that equilibrium can still exist in a smaller space because the left side does not need as much space. If we look at the next example, I've got a total of 2 moles of product gas versus 4 moles of reactant gas. So if we increase the volume, then we're giving it more space. This reaction is going to favor the side that takes up more space. It's going to shift to the left, so it's going to shift towards the reactants. If we give it less space, if we squeeze it, it's going to favor the side that needs less space, so it's going to shift forward towards the product side. Now, if the reactant side and the product side are equimolar, meaning they both have the same number of moles, then there is no difference shifting to the left or right because the reactants and products both take up the same amount of space, so there will be no effect in either case. So we've addressed what happens to gases if the volume is changed. And so the thing to remember is that pressure and volume have an inverse relationship. Okay, so we talked about volume, but what about pressure? If the pressure increases or if the pressure decreases, what happens is it's the opposite of what happens to the volume, right? Because increase in pressure is the same thing as decreasing in volume. Right? Decreasing the pressure is the same thing as loosening up or increasing the volume. So when you answer these questions relative to pressure, you have to keep in mind that inverse relationship. All right, and so the third type of stress is changing temperature. So whenever you have a reaction, a lot of times you will see a symbol like this, delta H. Delta H is the change in heat that takes place when this reaction takes place. And so a positive value right here, this is a positive value. The plus sign is not there, but there's no negative sign, so therefore it's positive. This is what we call endothermic. Positive values means that the reaction is endothermic, and endothermic means that the reaction takes in heat. If it was a negative value, like this one, this is what we call exothermic. And what exothermic means is the reaction releases heat. All right, so from a practical aspect, what that means is endothermic reactions, if it takes in heat, heat is considered a reactant. So you can just literally write the word heat on the reactant side. Exothermic reactions, since heat is released, heat is considered a product. So you could write heat on the product side. So now that we've got that established, if we look at the first reaction, if we increase the temperature, at which this reaction exists when it's at equilibrium, it's like we're adding too much heat, because we just said heat was a reactant. So now you have too much heat. Heat being a reactant, this reaction is going to try to move forward to consume some of this extra reactant. So it's going to shift it to the right. It's going to go forward. And if we decrease the temperature means removing heat. I should actually write over here for if temperature increases, I'm going to say increases heat. Okay, so if we decrease the temperature, we remove heat, and remember the system always responds to replace what was removed. So the reaction would shift left if you cooled it down. For the second reaction, this is an exothermic reaction. So being that the heat is on the product side, if we increase the heat, we are increasing the product. We have too much product. The system's going to try to redistribute all that, and it's going to shift left. And if we cool it down, the system's going to try to replace it, so it's going to shift to the right to replace the heat that was removed. All right, so should also mention that a catalyst, if we add a catalyst has no effect and does not shift the reaction. So we defined catalyst a while ago. A catalyst is it's something that speeds up the reaction but is not a reactant or product. Therefore, it does not appear in the equation. So adding a catalyst does not change. It does not shift the equilibrium left or right. And also, if we add something that's inert, so if I've got a reaction, A plus B forms 2C, for example, and if I added something like neon, well, neon is not a reactant. It's not a product, right? If I add neon's just going to sit around. It's kind of like a spectator. So there's no change, right? It doesn't shift it any which way. So you have to be aware if something is added, if whatever is added does not react in any way, then there's going to be no change. So let's do these examples. So here is my reaction for the ferrothiocyanate ion, and the KQ is given and the delta H is given. So which way does the reaction shift when If we increase the concentration of iron, right? Iron as in the iron plus 3 ion. If we increase the iron, we're adding more reactant. The system's going to try to consume this extra reactant. It's going to shift to the right. If we increase the temperature, now pay attention to the delta H. This is a positive value. So if it's a positive value, remember that positive values means endothermic, and that means heat is a reactant, so that would go over here. So if we increase the temperature, it's like increasing the amount of reactant. This is going to shift to the right. And the third change, decreasing the pressure. Well, these are all ions, and that means they are not gases. These are all aqueous. So no effect, because pressure and volume changes only affect gases. So how do the following affect the KEQ value? By the way, we mentioned this earlier in the unit, but only temperature change affects KEQ. So if we increase the concentration of iron, what that means is this reaction is going to shift to the right, like we mentioned before, but it's not going to change KEQ. But if we increase the temperature, we have observed that this is going to push it forward. And if it's pushing it forward, that means we're increasing the product and decreasing the reactant. And KEQ, only temperature changes can change KEQ. So as a result of this, we're going to have a higher KEQ value. And that is the only way to change it, is by changing the temperature. It doesn't matter if it's endothermic or exothermic, changing the temperature will change the KEQ value.